Well, good morning, everybody. Now that I'm slightly dizzy, is this a bad time to tell you that I have vertigo? I do.
Great time.
Yeah, I do. So standing on the top of that ladder is probably not that healthy. So I will now be dizzy for the rest of the lecture, which will make this really, really fun. Tomorrow's lab is not lab number 5. It's lab number 6 because, again, we don't do things in order with our lab manual. So lab number 6 tomorrow, it's going to be a lot of vector practice, which is really good because we're doing a lot with vectors and we're about to stop doing some stuff with vectors in chapter 7 and 8. But it's good to keep that vector practice up. So we'll be adding and subtracting and doing stuff with vectors tomorrow. All with a little table that you're going to then experimentally determine if your vectors are what you thought they were. Let's see, so there's that. Homework due this Saturday, right? Yeah, okay. So we're all on track. We, not to scare you initially right at the beginning of the morning, but we did this last time, right? And it like, if nothing else, the takeaway from this screen is that friction made it worse, right? It's just like more equations, more stuff to keep track of. But again, I keep trying to help you understand that it's process that saves you in this. It's that methodology of going through. And are you going to make mistakes? Sure. You're going to have problems with number 10 on the homework? Sure, yes. That's all normal. But if you're just kind of guessing and throwing equations at Newton's laws problems, you're doing it wrong. You really want to go through with process. So let's just continue the example train here. And we already did connected objects last time in chapter 5. So let's do it now and simply add friction into the mix, right? So I'm going to do a mass 1 right here, a mass 2 right here. I don't even remember if we even had, we didn't even have a situation for this one, did we? I don't think, okay. So we're going to know mass 1. We're going to know the angle. So if I'm going to add friction to this, I need to know something. Like, what do we know about friction? So kinetic friction, what is guaranteed with kinetic friction? What do you know? It's less powerful than static, but there's like a key thing about like which way it acts. It's always opposite the velocity, isn't it? Okay. With static, we don't know, right? Kind of what direction it's doing, what its strength. That's something we have to go kind of figure out. We can't really, we need to make assumptions, but we got to be really careful with the static assumptions. So let's do kinetic friction here, and let's say that mass 2 is winning in the sense that this whole system, and I didn't draw the rope. Why didn't I draw the rope? Right? This whole system, the system being mass 1 and mass 2 connected by a string. Let's say that it is moving, like we're told that it's moving up the slope and down. Now, it could be speeding up. It could be slowing down. It could be moving at constant velocity. I don't know, but when friction is involved, especially when things are sliding, we have to know which way they are going. And so for the purposes of this problem, I'm just going to say that's the direction. If it's not the direction, you'd reverse it and redo the analysis. If kinetic friction's involved in the problem, you need to be told that information. Yeah. All right. So what I want you to do right now is draw the free body diagram for mass number 1. Just like do it right in your notes, show each other, help each other out. For the next couple minutes, if you need help, like you're stuck right now and don't know what to do, call me over, and we'll get you started. But see what you can do about getting the free body diagram for mass number 1 down in your notes, or just on a piece of scratch paper. Just give it your best shot. Bless you. So do you agree with what I've got on the screen so far? Where did I get that? I got it from when we did it in chapter 5. Right? Okay, we did it, right? And so we know that there's got to be tension. What object is causing the tension? String. We know there has to be M1G. What object's causing that? The earth, right? What object is causing the normal force? The surface, right? They're in contact with each other, right? So I can name those objects. I'm feeling very confident that those forces exist, right? Yes?
Would friction be vector as well?
Yes, it is. I haven't drawn the friction on there yet, right? But since this thing's sliding up the slope, what direction would I put friction? I would push it down the slope. Because I know, because right, I told you guys that this thing is sliding, right? So it's going to be pointing down the slope. This would be kinetic friction. And you can, if you want to be very careful, right, you can say F sub K, right? Like I know that this is kinetic friction, okay? Just a what if, just to help you out here, okay? What if the block were sliding down the slope? What direction would we put friction? It would be pointed up the slope, right? And then the free body diagram would have a friction that points, right, along with the tension. Like, try not to get caught up in, oh, well, I've got to follow the tension, or I got to follow. You're not doing any of that. You're looking at the friction all by itself. Don't look at anything else, right? Which way is it sliding? If it's kinetic friction, it slides the opposite way. Okay, so if there were static friction, if this thing were not sliding, okay. Which way do you draw the friction? You kind of have to know something, right? Like if M2 were really, really big and that tension were really, really big, right? Then there's a lot of pull coming up this way, up the slope by the tension. What will static friction try to do? Counteract it to keep it from sliding up. But what if mass 1 were bigger than mass 2? What if the tension were not enough, right, to keep this thing held up against gravity? Static friction could flip and go the other direction. So when you have something that's not sliding, you have to be more careful, and it can often be confusing, but what, how do I know what it's doing? There'll be language in the problem or the situation that's like, what is the maximum static friction that this thing could have, right? Maximum static friction would probably be like when the tension and the friction are opposing each other, right?
If I was trying to find static friction, and let's say I got a negative number, would that mean that I picked the wrong direction?
It could. It could. Not necessarily. Static friction is a bear. It really is. Okay, so oftentimes a problem might even just tell you, right, that the static friction is directed such and such. And if it doesn't, then there probably has multiple parts that's asking you to consider, well, what if it points that way? Okay, now solve that problem. Okay, what if it's the other way? Usually one of those will be called a maximum and the other one will be called a minimum. So the problem is, the answer is the worst answer you can have in physics. It depends. Okay, you don't want your teacher to. Well, it depends, right? Because then there's too many choices. And I wish I could teach you more specifically about static friction, and I can't. It literally depends on every situation that you have. So, all right, but let's continue with this one. It's why we tend to go for kinetic friction. Although I think I was mean and gave you some static friction ones too. All right, mass, we don't have a coordinate system for mass number 1. Now the acceleration, does the acceleration have to be in the same direction as this velocity? No, it could be speeding up or slowing down or not changing its speed. We don't know, we're not given anything. We're given m1, m2, theta. You guys like to have numbers, right? It's your preference, so I'm just gonna give you numbers. Let's 1.5 kilograms. 0.5 kilograms, angle 25 degrees, that's not a degree symbol, degrees, and a mu of 0.2. What's mu again? Coefficient of friction, right? Okay, so let's see. Should we just say A is up the slope? This is a complete guess. We're trying to find it, right? And so if I guess that the acceleration is up the slope, and I'm wrong, if I find out that the acceleration is in fact down the slope, and I guessed that, well, what answer am I going to get for the acceleration? I'll get a negative value. And then, now I'm guaranteed to know that I just picked the wrong direction for acceleration. Because acceleration, its positive direction is very arbitrary in these problems, whereas static friction's direction is not arbitrary. It really depends on what's going on. I just made up numbers. Yeah, people have been complaining that the symbols are too much, so give us numbers, mister. Okay, well, there you go. You can give me numbers. Not that the numbers matter at all. Okay, in terms of solving the problem. They're just things we put in at the end. All right. Mass 2. Is there anything different for mass 2 from the last time we did this? Is mass 2 affected by any friction? No. So we're still going to have down, tension up. Woo, quiz coming up. Which way are we going to call positive? I didn't finish my thought over here. I got the acceleration. So I'm just keeping King's consistent, and we'll call positive y being down over there. Components. Which force needs components? Yeah, it's that M1G force, isn't it? It's always, we're going to do an example here today where this isn't the case, but M1G cosine theta right there, M1G sine theta, because that's where the angle is. We've seen that before. Okay, and so really the only thing we've added to this whole setup is that friction, right? That kinetic friction acting backwards. So what is our Newton's second law going to say? I do like to kind of get it down on the page and then have some sort of organization, right, for what's going on. I didn't mean x and y there. I meant m1 and m2. So in the x direction, m1a. I'm not going to write a1x. I'm getting tired of that. In the y direction, I'm going to write I'm not even going to write m1. Well, I'll write m1a. But what am I going to say a is in the y direction for mass? The acceleration in the y direction for mass 1. Yeah, we remember we make sure of that when we set stuff up. Okay, mass 2 in the x direction. I already know that 0 equals 0. And in the y direction, I have m2a equals. Okay, so that's kind of like my template here. That template isn't always that. I mean, m2 could have x components if it was sitting on another slope or something. But for something hanging in the air, I know it's going to look like that. All right. Forces. We got to do forces now, right? X direction only. Remember, we're just looking along this line right here. Okay. How many forces are there along that line? There's 3. What are they? Tension, friction, m1g sine theta. Okay, go back for their signs. Tension. Why? pointing up the slope, and we called up the slope positive. We don't have to do that every time. We can do down the slope positive, right? Friction, pointing down the slope, and m1g sine theta, pointing down the slope. All right. In the y direction, looks like I've got normal, m1g cosine theta, and check me, did I do it right? Looks like it, right? Normal is positive because it's away from the slope, and negative m1g cos theta. Didn't mix my trig functions. I'm doing pretty good for being a little bit busy. All right. For M2 now. Which one of these is a positive force? The M2G or the T? It's M2G. Good job. Good job. M2G is the positive one, and T is the negative. Why is T, even though T points up, why is T negative? Because we said that positive was down. We're following our guess for the acceleration, right? Go with that direction. It just makes keeping track of your signs a lot easier. Okay. Oh my goodness. What have we got here? Did you say art? Okay. Should I put it up on Instagram and start selling? Good, right? It looks like I have, now I've got to move into problem solving. Okay, so we are looking for A, right? A is what we want. Better write that down. A is what I'm looking for. I don't know T. I don't know A. I don't know F. M1g sine theta I do know. I don't know normal force. And it looks like everything else is like these are repeated things, right? Okay. So I have 4 unknowns, A, T, F, and N, and 3 equations. Yes! Don't forget how fun this is. Does anybody recognize this problem yet? What is it? You've done it before. Very close to it. This was question number 5? 5 on lab number 1. It's amazing how things in this course come back to haunt you, right? Okay, right? I believe that we simplified the one in the lab slightly, okay? Because I think the problem you had, I pulled it up on my screen here because I had to get the numbers. I think what we gave you was T minus F equals M1A. Yeah, and then N minus M1G cosine theta equals 0. We gave you M2G minus T equals M. Did we write it like that? Yeah, M2A. And then we gave you that. I think the other teacher wrote this. He wrote it slightly different, right? Okay. But you'll see here, right, that we took off the M1G sine theta term, because we were just really kind of testing to see if you could do algebra, right? Okay. And then the numbers I gave you are exactly the numbers we gave you in the thing right here, okay? So you've done something very close to this before, mathematically, right? But as you can see, there's a lot of setup that goes into this, right? So if we're going to solve this, and I don't want to belabor the point too much here in the algebra, but how do we go about solving, like getting rid of the things we don't want to know? What do we not want to know? We're only asking for acceleration, right? So we want to get rid of F. Get rid of, and by I mean like mathematically substitute away so it's no longer in our equations, right? I want to get rid of F. I want to get rid of T. I want to get rid of N, don't I? Those are 3 things I don't know, but I really don't care about. Unless it was like a homework problem, they annoyingly would be parts A, B, C, and D, right? Find all those things. So I'm gonna, my plan of attack here, right, is to take this normal force equation, solve it, and stick it in there. And then when I have that, I'm going to stick that in there. And then I'm going to solve this for t and stick it in there. And hopefully I only end up with a's. Sometimes you have to lay out your strategy, right? Sometimes you have to like kind of visualize with arrows just what the heck you're going to do mathematically to this. Okay, so let's step back for just a second. You guys now know that since I'm spending time on this in class, how likely are you to get something like this on your exam? Very likely. How long has it been taking you on your homework to do a problem like this? Forever, right? So, Mr. Balogh, you're only giving me 120 minutes to do 12 problems. You give me one of these and I'm dead. Right? Fair. You can expect to have problems like this on the exam. That's not going to change. But I can tweak the problem to make the algebra really short. Right? I can still find out if you know how to do a free body diagram and set it up and communicate that you know how to apply Newton's second law. I can test all of that, right? And then make the algebra really short by giving you the tension, right? And then boom, all of a sudden, right, this becomes 2 equations with 2 unknowns, and I expect to be able to do that faster, right? So I will do that on the exam. I know I'm only giving you, on average, 10 minutes to do a problem, right? So I'll try to set it up, right, so that the math can go fast. And or sometimes I've even said, don't solve the problem, just write down the Newton's second law equations, right? And then I'm really just kind of grading you on your setup, okay? So realize that I do know that I'm only giving you 10 minutes on average. I would say that this problem is at least a 15-minute problem, right? Which means there has to be another problem somewhere on the exam that saves time for you, right? So you're trying to hit an average. So you want to try to, in your practice, like the thing that you're sort of aiming for is to be able to look at these problems and quickly get a free body diagram down, knowing that you've covered like all your bases. And how do you know that? I'm brand new, Mr. Bell, I don't know what I'm doing. Remember I told you the key thing is to identify objects. If you can identify the object, then that force is real. If you can't, there's a chance that you've made up the force, right? And then practice getting these equations written down. And it's that practice that will make you faster, okay? That will give you the confidence. If you're just sitting there, oh, well, I'm just going to copy paste like this problem onto this problem onto this problem, you can get lost really fast and you end up spending brain time and effort on things that aren't going to get you anywhere. All right. Dad mode off. Let's solve this thing. Let's do what I said. So the normal is going to be m1g cosine. I'm going to do this really fast. Cosine theta. That n goes into this s, so now it's mu m1g cosine theta. That f is going to go up into this equation, m1a equals t minus mu m1g cosine theta minus m1g sine theta. I'm just to bring this home, when I solve this for n, I'm no longer seeing m1g cosine theta as separate things. m1g cosine theta is a number in my head. I don't know what number it is, but it's a number, okay? Because I know m1, I know g, and I know cosine theta. Those are all things I could put in my calculator. So I stop seeing it as separate things, and I just see it as a lump thing, right? And it just goes along for the ride. Same thing over here. F is now this number. It's a lot of symbols to represent that number, but it's just a number, so I can plug it in to wherever I've got it. I don't know if that helps you with your algebra or not. This is going to be m2g minus m2a. Swapping things across equal signs changes their signs, and then that t gets inserted. m2g minus m2a minus mu m1g cos theta minus m1g sine theta. Mr. Balogh, why don't you just put the numbers in, because numbers hate me. This m2a is going to go over here. 1 plus m2, factored out the a. I'm left with all the other numbers that I had before. That's an m1g minus m1g sine theta. Divide both sides by m1 plus m2, and there's my a. So again, I did that algebra really fast, right? I could go and check this thing. It'll be very close to what you guys got on number 1, right? Which is, we had the extra m1g sine theta in this example. Wow. With no friction in this problem, we had 2 equations with 2 unknowns. That was it, okay? We were able to safely, like, we didn't need the y equation, all that kind of, for math number 1. Friction really amps up the difficulty pretty fast, right? And so, yeah, be careful what you wish for, and stop making fun of physics teachers who keep ignoring things like air friction. There's a reason we keep doing it. I don't need to be honest with you. You know I'm always going to be honest with you. I really feel like this is peak difficulty in this course. This is a lot. It's a lot of things to keep track of. And you need to know that you've been like climbing this hill, okay? Coming out of kinematics, and it was, yeah, it felt hard, and now we're like we're going to get on top of the hill, and we're going to level off for a while, okay, in the terms of the difficulty, and then eventually start coming back down at the end. There'll be little bumps along the way, but really, of all the things we ask you to learn, and all the things we ask you to bring together, and all the disparate ideas, like, look at this thing. You have to have, like, sketching ability. You have to have conceptual ability to get the forces down, right? You need to have, like, the ability to work in symbols. And I'm not just talking about mathematics. I'm talking about, like, writing down and applying Newton's second law correctly and getting directions. There's tons of stuff to keep track of here. And then on top of all of that, we then ask you to do a math problem. I'm not going to apologize. I mean, it's not my fault. You signed up for the class, right? Okay? But I get it. I understand. And I think one of the more frustrating things that you are up against, and you don't realize it, is you come into class and I waltz in here and for all the world make it look like the simplest thing to do. No problem. Just throw the thing and right? Okay? And then you're like sitting there going, oh yeah, okay, I get it, yes. And then you leave class, you go home, start doing your homework, and what happens? I have no idea what I'm doing, okay? Never ever compare yourself to me, okay? You are so much better than me. I just have the advantage of doing this as my day job for the last 24 years, right? Okay? I've been around the block a few times. And so, yeah, I walk in and make it look easy, right? Of course I'm going to be fast at it. You're going to struggle. And it's okay to be struggling, right? It's okay if you're training for a marathon to not be able to do a marathon for a while, right? Okay? You'll get there. You'll get there. The question is, how fast can you get there? So, please, I know several of you have been expressing sort of that frustration, but Mr. Balogh, I leave class and I forget everything. Of course you do. Okay, you've seen it once, right? You need to see it over and over and over again. Let's do a quiz. Let's take your brain and tweak it. Whee! Now we get to go wee. Okay, so this happened This happened when we did kinematics. I don't know if you remember this. We did all of this kinematics and then sort of at the very end threw circular motion at you. That objects going around a circle at constant speed have a constant acceleration pointing toward the middle. So we're doing something very similar here. We've covered Newton's laws, 3 laws of motion, and we've kind of got that toolbox that's at least opened now, and you've seen the tools. Some of you have started touching them. Others of you have still not started your homework. Nah. Right? Which is bad. But we're going to, again, put circles into the mix because your author decides to do it this way, and it's okay. It works fine. Why do people ride roller coasters? Because it's fun, right? It's fun to be hurt and slammed around and go upside down and go weak. So the question is why, like, what is it that somebody's seeking when you go ride a roller coaster, right? Like, what's fun about it? The adrenaline rush of thinking that you're about to die. Yeah, they make that as loud as possible, right? Right? Just to ratchet up the stress, right? Get the blood pressure, right? Okay, and then you get to the top, it's like, there's no more ching, 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 go get it, ah! Right? Right? Okay, so it's fun, right? But we're going to try and remove all of the fun by applying some fun, right? But actually, we're not going to do friction in this case. Okay? What we want to do is we want to apply our ability to think about forces and Newton's laws to really kind of answer the question. What is it about this situation that people experience, find fun, what's going on? And the way we're going to do that is with this approach called the vertical circle. Okay? So I need a circle. Luckily, I have a bit of a drawing tool that might make it so, you got a circle. All right. What we're going to do, and I fully realize that the picture I provided for you over there does not look like a circle, right? That's a teardrop. More on that later. We're going to do perfect circle. And we are going to take a look at 2 situations for riders, or this could be the person in the roller coaster car, it could be the roller coaster car, it actually doesn't matter. We'll do the person, okay? And we're going to draw free body diagrams for what a person is experiencing at the bottom of the loop-de-loop in a roller coaster, and then we're going to draw the same thing, but when they're at the top and inverted in their loop, okay? So that's our goal. We won't draw the sides. We'll just do the top and bottom. Okay, so we've got circle. We know something about that circular motion, right? We know something about what the acceleration is doing in that circle. Which way does it point? Inwards, right? So this is kind of interesting. That means that at the bottom, which way is the acceleration? Towards the center of the circle. The acceleration is going to be up, isn't it? But at the top of the circle, which way is the acceleration? It's pointed down. Are we going to have 2 different definitions for what positive means here? Yeah. Okay, right? It's really 2 separate free body diagrams, isn't it? My drawing's a little bit small over there, so I'm just going to kind of recreate, okay? This is for the bottom. We'll do the bottom first, okay? So I'm just going to pull the rider out so I can get a little bit more room in here, make it a little bit more clear about what's going on. At the bottom, I do know that my acceleration is pointed upwards, and so therefore I'm going to call positive y upwards. Name all of the objects that are pushing or pulling on a rider on this roller coaster. We are ignoring air. And the track is frictionless. So gravity is coming from the earth, right? And then some sort of contact, right? This person's rear end is in contact with the seat or something, right? They're touching each other, aren't they? Right? So we got a normal force, right? And I mean, if I wanted to be really careful, I should probably have drawn that normal force longer, right? Because I know that I have to have a net acceleration upwards. Are there any other forces? What question should you be asking right now? What objects do I have, right? Okay. That's what you want to be talking about. Now, some of you might be like, well, Mr. Balogh, I've ridden a roller coaster where they put the thing over your chest, right? Well, isn't that like pulling me down? We can sum all of those contact forces that even like the shoulder harness and the seat and everything as a normal force, right? As the force of contact. We can divide it up if you want, but it gets more complicated.
Would another force be the tension force between cars, or are we just going to do single car?
This is on the person in the car, right? And even then I would just do a single car. But yeah, I mean, in reality, there's the cars pulling each other, right? There would be friction between the track, right? And all that kind of stuff. But do any of those forces point towards the center? Like friction, if we had it here, which way would friction be pointing? Like perpendicular, like opposite the motion everywhere, right? It's always going to be like tangential to that circle, perpendicular to the normal force. And so like that's not really causing circular motion at all. It's causing it to speed up and slow down as it goes around the circle. But I want to focus on the forces that are really contributing to this circular motion.
Why is the normal force greater in this case?
Because we have to accelerate upwards. And I don't have any, that's all I got. I don't have any other objects pushing or pulling in the vertical direction here, right? That's all I've got. So I know the normal force has to be bigger, okay? All right, and I specified positive y as being upwards. Why did I do that? Yeah, right? It's just, that's the way the acceleration is going. Okay, so here at the top, I should have reversed those diagrams, shouldn't I? You're going to hate me. I love electrons. I'm sorry if you got it backwards in your notes and you're doing it on paper. All right. But this will make more sense in the end. Okay, so now at the top, which way is gravity pointing? Does that change just because you're on a loop-de-loop? No. Which way is the normal force pointing? Down? Why is it pointing down? Because you're upside down, right? The plane of contact, right? It's that feels uncomfortable. Okay. But, I mean, there's really no other direction that normal force can be, right? Yeah?
Would the normal force be longer than the gravity?
In this case, it doesn't matter, okay? Because I know my acceleration is downwards, and I've got two downwards forces, right? So I'm unbalanced in the downwards direction, so I don't know what the relative amounts are. It could be less, could be more. Actually, I do know it's going to be less, but... Ah, very good. Why would positive y be going down? Because that's the direction of the acceleration, right? Got to be careful there. All right, for the, let's do the top first. Okay, so for Newton's second law for the top, ma equals. You tell me what to write. Positive mg, okay. There's no cosine here. I don't see any cosines. Where did we go wrong? I think we went wrong in not trusting the method. First thing you should do is write down the forces that you have. What forces do you have in the y direction? mg and n. Leave a space, right? Now go back and do their directions. What direction for mg? Positive, because it's down is positive. And n, also positive. Never had to talk about cosine thetas or anything else because there aren't any components in this problem, right? You're looking at me with slightly blank stares. Yes? as you go upside down in a roller coaster, which way does the roller coaster car push on your rear end? It pulls you up. There's only one way that you sit on a seat. Isn't it amazing how physics makes you forget like everyday things, right? You sit on a seat, right? Which way does this surface push on you? Up. If I turn this whole thing over, it still pushes on me, right? Okay. I think the real question you need to be answering is, why do I not fall out? Right? If all the forces are pushing down, why don't I fall out? Name the force that keeps you in the roller coaster car. There isn't one. What keeps you in the car? It's inertia. You want to go which way? You want to go in one direction. You want to keep doing what you're doing. This circular motion is causing you to not do that. You want to go straight. Roller coaster car is forcing you to go in a circle. I think we need a demonstration. I'll be right back. All right, I found as many spherically round bouncy objects as I could, okay? Right, and I put them in this bucket. Right? What happens if I turn the bucket over? They just fall out, right? I will not demonstrate that because I don't want to have to go pick them up, okay? But here we go. You're over 50, you got to warm up a bit. All right, here we go. Right? Right? Okay. Doesn't come out, does it? Right? Would you guys put those away for me? I'll be right back. Emergency demos. What's that? Yeah, get the mop ready. Hope that's enough. Okay, how we doing here? Oh, thank you very much. Thank you, thank you. Will you verify that there's water in the bucket?
Yes.
Even though everybody saw?
Verify.
Yeah? Okay. Are we ready? See if I can do this. I might get really wet. Okay. Here, oh, I'm not worried about that. I'm worried about stopping. Keeping it in is no problem. It's getting it to stop and not splash out that's really the problem. Here we go. Let's try it again. Woo! If you get too slow, it'll come right out. All right, so we will not push that. I've climbed on a ladder today. I have tried to get wet. This is a good day. All right. So have I established the answer to the question? Things are pushing down, right? And really, like for the water or the balls or anything, right? That bucket can only push down, right? So try not to invent things that are like, how badly do you want to do just, right? There's something that holds me in. Okay, name the thing. Name the object external to the car that's pulling you up. No. There's nothing there. Okay. Bottom. Oops, wrong color. Okay, so now we've got mg and n. Which way is mg pointed? Negative. And then n is positive. What happened there? Y is going upwards with the acceleration. I don't have time. Okay. So so what? What is all this telling me? Let's solve both of these for the normal force. So if I solve for the normal force up here, this is going to be ma minus mg. I move the mg over, flipped its sign, and then reverse the directions of things. Down here, I get a normal force that says ma plus mg. Okay. Normal force. What's normal force? What's the normal force? It's the force of contact between two things, isn't it? One object comes into contact with another, right? There's going to be this force perpendicular to the surface. Okay, it's the force of in this problem, it's the force of contact between the rider's rear end and the seat of the roller coaster car. Where, top or bottom, is the normal force the largest? At bottom? Why bottom? It's ma plus mg, right? And at the top, there's a minus sign between those two things, isn't there? So what is a person's normal force going to do in a roller coaster? At the bottom, it's going to be bigger than it is at the top. Okay, so what does that mean for the experience of a person in a roller coaster? If they weren't going around in a circle, if A were 0, right, and this moving in a straight line, then in both of these cases, we would basically just say it's the weight, right? Weight's the only thing acting on them. But they are going in a circle. In fact, we know what that acceleration is. That acceleration is the centripetal acceleration, isn't it? Which is the the velocity squared divided by the radius of the circle. That we got that out of chapter 4. So we can put all that in there and we can solve for stuff. But more fundamentally, okay, a person will experience more normal force. Now, when you ask somebody how much they weigh, they often report to you what the scale tells them, and the scale only reads what? If the scale exerts a force upon the person, then that was terrible. Okay? But was there any earth in there? No. Was there any gravity in there? No. The scale can only tell you what? Normal force. The force of like you push on it, it pushes on you. That's all it knows. Why is it equal to your weight? Because your bathroom is not accelerating. Okay, normal force can equal weight if you are not accelerating. But if you are accelerating, like going in a circle, Now, whether or not your bathroom is accelerating, I guess depends on several factors. More primarily, how much fun you had last night. But like, usually they're not accelerating. So then it tells you to wait. But a person who is an accelerating frame of reference, who experiences this, will come off that ride telling you that they felt heavier at the bottom and lighter at the top. That's why roller coasters are fun, right? It's that changing perception of one's weight. Is their weight ever changing? Are we changing gravity just because you go on a roller coaster? No, we're messing with what you think gravity is by playing with the normal force. Normal force is less at the top, bigger at the bottom, and you feel that in your stomach, in your Yes. Okay. Now we get to the teardrop shape. Okay. Before we get to the teardrop, is there a speed? Let me ask the question this way. If there were nothing to hold the person in, if all the safety, this is like the worst nightmare, right? All the safety systems fail, there's no seat belts, nothing, right? Will the person stay in the car? Was there any safety belts on the water? Each water molecule didn't have its own safety strap. Okay, right? Okay. So there is a speed where they will stay in. But is there a speed where it might be too slow and they fall out? Yes. What condition must be true if the person is falling out? The normal force has to be equal to 0. Why equal to 0? Because now there's no contact, right? Falling out, by definition, means rear end no longer attached to seat. It only could happen at the top, and it can't really happen at the bottom. So if we say if normal force at the top is equal to 0, right? Then we have ma equals mg. Oh, rider's mass doesn't matter? No, apparently only rider's height matters. Okay, v squared over r for that acceleration equals g, so v equals the square root of r times g. There it is. That is the minimum speed required for a rider of a roller coaster doing a circular loop to not fall out if there is no safety belt to hold them in. Some roller coasters try to design themselves to get as close to that as safely possible so that a person in the seat does sort of feel. So if you have a roller coaster that does come over your shoulders with that harness, they're playing with this, okay? Because now they know that they can hold you upside down from your shoulders, right? But it can be really uncomfortable to put your entire body weight on your shoulders, and so they'll still try to tune it so that there's still some contact force between your rear end and the seat. Why is that one teardrop shaped? That speed only gives you that sensation at the very top. Okay? Either side of the very top, you're still in contact. By elongating the radius of the circle at the top and sort of shortening it at the bottom, you can pull off two things. You increase the amount of arc where a person feels weightless or feels like they're falling out, okay? It makes it from one point at the top to like basically a lot of points. Because basically at the top what's going on there is you got a lot of circles, okay, that you're at the top of. The radius of that curve is changing constantly, okay? The second thing is it makes the entry and exit of the loop much less violent. right? You're coming in at a nice angle, and then you extend the amount of time that they're sort of in that free fallish situation. And then as they come back down, it's not like this collapsing spine, right? Okay, as you get to the bottom. Some roller coasters, original roller coasters, did have like perfectly circular loops. They're not nearly as comfortable as teardrop shaped ones. Isn't that fun? I asked the internet for examples of bank turns, and this was like the number 2 picture.
What's the number 1?
If public transit were like that, sign me up. Right? What? Why is that bus not falling over? Yeah, if it weren't moving, what would it do? It would fall over, wouldn't it? We've got to find out why. We've got to find out just what the heck is... Oh, I forgot about that video. Where is it? I'm going to totally run out of time to do this one. That's all right. It is. I just had too much fun today. I got water and buckets, and things happened. Ladder. Oh, I did. I lost like 4 minutes. We'll blame it on the ladder. A student of mine a couple years ago who grew up in India sent me this. Yeah, don't just press the brake. Don't just press the brake. Like, what the heck is going on here? How are they able to stay up on the side like that? Well, yeah, physics is the answer. I mean, if those were all 4A students, A+. Why are you just... I don't want that one. Let's do that. Okay. So, how do I do... I know I'm going to run out of time. I'm going to start setting this one up, and then we're going to leave you hanging. You might not be able to do one of your homework problems. We'll see. Oh, no, because Chapter 5 is only due this weekend, right? Yeah. Not Chapter... See, I think of Chapter 5 and 6 as being the same chapter. Okay. What have we got? Normal force, mg. What have I just drawn here? This is a cross-section of that banked thing that they were driving on. So basically, that's the car. The box is the car, and it's driving out of the screen. Do you understand what I'm saying? Okay. So they're driving out of the screen in a circle. It's a horizontal circle now. I've got gravity caused by the Earth, normal force caused by the car that's right in the thing. Which way is friction acting? Okay, so there is like a motor force acting out of the screen and a friction acting into the screen. But is that helping with the circle in any way, shape, or form? No. In fact, if they're going at constant speed around the circle, those two forces cancel each other out. And effectively, we have zero. There's no acceleration now. Okay, let me ask the question this way. Which way is this thing accelerating? This thing is going around in a circle. a horizontal circle. Do I need to swing the bucket in a horizontal? No. Which way is the center of the circle? It's towards the right, isn't it? So the acceleration here is towards the right. Because the circle is a horizontal circle, right? The plane of the circle is right here. So the acceleration is to the right. The friction keeping that thing turning, oops, back. It's pointed that way. When you, top view, flat turn, just a flat turn, okay? There's you in the car, right? Okay? So it's like a drone's eye view, okay? What direction is the acceleration if you're doing a right-hand turn? Towards the center. So to the right, okay? But towards the center always, right? What direction is the friction pointing? Well, okay. Yeah, okay. So there's a motor force and like an air resistance or rolling resistance. We're not talking about those forces. We're talking about forces that you guys are doing good thinking about them. But those two are going to cancel each other because this thing goes around at constant speed. I'm asking about the force of static friction between the tires and the road. In and out? There's only one answer. Towards the center. Why do I know it has to be towards the center? Which way is it? What force is keeping your car in a turn? No, inertia wants to do what? Go straight, right? But we've turned the wheel of the car. We are now turning to the right. Name the force that is turning you to the right. There's only one that connects your car to the road and keeps it from skidding anywhere. Friction. Which way is the normal force pointing? Is that going to turn you to the right? No. Which way is gravity pointing? Is that going to turn you to the right? What's left? And yet, how many of you were ready to swear up and down that when you turn to the right, there's something that pulls you to the left? Why would you think that? Because that's what happens. Mr. Balogh, I got the hood. Why do you feel pulled to the left? Because you have inertia. Which way do you want to go? Straight. Which way is your car going? To the right. The car is turning from underneath you, and the driver's side door comes in at you. Everything's pulling you to the right. That's where the real forces are. Everything else is made up. Name the object that pulls you to the outside of the turn. Inertia is not an object. No ropes, no rockets, no ghosts. Nope. There isn't one. We will continue this discussion next Monday. Okay? And I'm going to start chapter 7. I'm going to do this and we're going to start chapter 7. I'm probably going to do 7 all in one day.